Okay, so basically today should be the last class where we learn new things. Okay, but it's going to be one of the coolest one. So today we will look at this application of Minimax theorem. So last time we learned about what is this theorem, right? And today we will see how useful it is. So before begins, let me just set up the notation a bit, right? Just to remind you, for any number n, I will let this thing, data of n, or simplex of n, it's just like the thing that contains, the set that contains our distribution of n objects. Okay? So when I say that, okay, P is in data n, it means that P is a distribution over n objects, like n experts or something like that. And actually, for any set S, data of S just contain the distribution over all elements in S. So that's the notation. And now, so let's recap what we have from last time. First, we talk about two-player zero-sum game, right? And for two-player zero-sum game, it is described by just one matrix, A, which is a payoff matrix, when there are n rows and m columns. Okay. And so basically, max player will choose the distribution of row x, and min player choose distribution of columns y, right? And then we compute the expected payoff. I will let like a of xy be the expected payoff when max and min choose this distribution of their strategy, right? And axy is can be just computed in this way, x times a times y. Okay? This is just an expected payoff. Okay? And then if also I will use this notation, if x here is just instead of distribution over rows, just choose one row I, right? If max choose one row I will just use this notation a I y, where max player choose the ith row. So the expected payoff is this thing, ei times a times y, okay? Which is just like summing over all j, aij, yj. Similarly, if min player choose j deterministically, the expected payoff is this thing. So one thing that I want to stress is that when you see axy or aiy, you need to be careful which one is a distribution and which one is not a distribution. Okay, if this one is not a distribution, it means this thing, and y is the distribution. So it's like a summing over all y. Yeah. Okay. So we'll use this notation quite a lot in this class. So make sure you understand this notation. Yeah. Okay. And now, given this notation, right? Well, we talk about max min of a game and min max of a game. So we talk about max min of the game. So what is this? The meaning is that max min of A is the best payoff that max player can get if he is forced to play first, right? So, and it's defined to be max of x, min of y, axy. And the way note that the way you interpret is that it's like max player try to choose x, right? The distribution of row, such that it maximizes this whole thing. It maximizes the best response from min. That's the best thing max can do. You try to choose x, the distribution of row, that maximize the best response from min. And know that the best response from min, if x is given, then it will be deterministic. Right? It can be deterministic. Like min can just as well choose one column, j, that minimize whatever max is, like minimize the expected payoff once x is fixed. Right? So this is what is max mean. The best payoff of max if he need to pay first. Similarly, right? The best payoff of min, if she need to play first, is just the flip side of this, min max of A, which is min y, max x, ax y. That is, if you interpret this, it's just min player need to choose y such that it minimizes this whole thing, which is the best response from max. And last time, we see the Minimax theorem, which says that for any matrix A, min max and max min and min max are the same. And that we will use, because they are the same, we can define one number associated with any game, and we will call it the value of the game. So that's just the value, the best payoff of both max and min that they can hope for. So given any game, we know exactly if max and min want to optimize their utility. There is just one number. The best they can hope for both players is just the value of the game. Okay. So that's from last time, and let me recap further. So we know that this is the same, and the way we show that they are the same is not just to this is not just some existential proof. We give an algorithm, right? Such that we give an algorithm to compute to give an algorithm to construct a strategy for both max and min, such that it's the best strategy for both of them, and prove this thing. So let's recap. How did we do it, right? So to get we construct an algorithm to get this near optimal strategy. And how did we do it? We just let two player, one player being use one player choose the distribution of strategy by following weight update algorithm. Another player just be greedy, and then let them play for some rounds. And at the end, just take the average of the strategy that they have both been playing so far. So, for example, we see this one where max player is greedy and min player is just weight update. So given A and epsilon, what we do is just, okay, we have some number of rounds. Min player just choose the distribution of columns according to weight update, according to the weight, proportion to the weight. Once min player choose this distribution, max player just be greedy. Just try to choose the maximum row, that the row that maximize the expected payoff given yt, given what min choose. Right? So that's what they do. One player just be weight update, one player just be greedy, and then once that is done, then the weight update player need to update its weight. And how did we update the weight, right? So min player choose the distribution yt, max player choose a row it, and then we just let this row it be the loss vector for the min player. If some entry lost a lot, if the loss is big, then the weight is decreased a lot, and so on. And at the end, well, once like you have done through this iteration, like once the weight is updated, then go to the next day and repeat, right? And after you have repeated for some days, like just log n over epsilon, then what you do is just, well, the max player just take the average of everything that they have chosen so far, that he has chosen so far. The min player just take the average of the strategy that she have done so far, and we just return the pair of x and y. Okay, so this algorithm is what we talked about last time, but question about this actually? Okay. So it's just like some algorithm that like they kind of play against each other, and then both strategy will converge. After averaging, the strategy will converge to something good, right? And in each iteration, like you just need to compute like the non-trivial thing that you need to do is just compute the argmax of this thing. Just try to be greedy. Everything else is just weight update. Like given yt, which row is the best? Now you can talk about like just a symmetric algorithm. When min player is greedy and max player is weight update, right? So here, like max player will choose the distribution of row according to weight update. Then min will choose the best column, respond to this strategy xt. So choose a min column, respond to xt. And that column, you think of it as a gain, like that column will be a gain vector for the max player, and max player will just update the weight. Well, just the same thing like before. So just switch the row. And because everything is really symmetric, so like they really guarantee the same. They guarantee the same correctness. That is, given any payoff matrix A, this should be R. Both algorithms will return x and y, right? Such that x is the best strategy for max and y is almost the best strategy for min. That is, this is a payoff of max player when they choose x, when you choose x. This payoff is almost as maximum as possible, which is the value of A minus some like additive epsilon, with some additive error here. Also min, y is the strategy for min, and this is like almost the best because it's almost as small as the best thing she can hope for, plus some error here. So that's what we showed last time. And now let me try to like interpret, like put this into more perspective. Well, like because the way you think of these two algorithms, right, is that you can think of it as a reduction. That it reduces the problem of computing additive approximation of both min max and max min. Like, so this is a problem of finding the best strategy for max. This is the problem of finding the best strategy for min player. So this is a min max min problem and min max problem. Well, if you want to solve this problem up to some approximation, the two algorithms say that it's enough to just like it reduces these two problems, right? To just computing either one of these. So if you use max greedy algorithm in each round, right? What you need to do is just to choose the best response for max player. That is fine, like given like some distribution that min player fixed, just choose argmax, best row, best row I such that AI is maximized. Or if you use another algorithm, mean greedy, in each round you just need to solve this problem where like you fix x, the distribution of row, and you just need to find the best column according to x. Right? So you reduce the problem of solving two things to one of things that you can choose. Like either you'd want to choose whether like you think like finding max is easier or finding min is easier, you can do. Just solving one of them, you will get two of that. And what's the running time? If you choose like a max greedy algorithm, each round you need to solve argmax. The total running time is going to be this thing. There are this many rounds. In each round, you update the weight of the min, like update the weight among the column, and in each round you solve max greedy problem, finding argmax. Symmetrically, if you choose min greedy algorithm, then you take this many times, this much time. Okay. So does this make sense so far? Right? You think of it as a reduction. When you want to solve, when you find a problem that is like a min-max problem or max-min problem, it's enough to just solve one of problem. And this actually, like conceptually, this significantly simplifies the problem, right? Because the problem of min-max and max-min, like, is a problem with two quantifiers, and you just reduce it to just max problem or min problem, just one quantifier, much simpler. And you will see in action how much simpler it can be, like today. Okay. Let me actually skip this thing. Okay. So what we want to do is like we know this reduction now, right? And we will try to exploit it. So my plan is this. What I want to do is like I will start by defining some simple game, like just certify the zero-sum game that look innocent, look simple, and then we'll try to interpret this game together, like show that like argmax, like solving a max-min problem of A. It turns out that from this game it will be capturing some nice and well-known problem. On the other hand, like if you look at min-max problem, it's just going to be the dual of that problem. Okay. And okay, so like given some game, you get like a nice problem that is important, and to solve that, both of the problem is now enough to solve one of the like argmax or argmin problem, and this like a problem with just one quantifier will be much more simpler. And it means that it's enough to solve some simple problem and to get a solution for like these two nice, like a big, harder problem. Okay. So let's start with the first game today. The first game that I want to look at is this game, the game between path and edge. Okay. So imagine that there is an edge, like there is a graph with S and T, right? And now one player, an edge player, choose an edge. And then like an edge player here, right, is a max player that chooses an edge in the graph. And then the path player will choose an ST path P. Okay. And the path player will need to pay to an edge if like the path goes through an edge, if an edge is in the path. So you can think like, okay, you need to go from S to T, and this edge is like a toll station. You need to pay if you go through it. So with this, you get a payoff matrix, right? Such that the row is for each edge and the column is for every path. So this is a huge matrix with like exponentially many columns. And you get that like an entry for an edge E, and the path P is 1 if an edge is in the path. So is this game clear? Right. So now let's see what is min-max of this game. Okay. Let's interpret what is min-max of A. So all we need to do, right, is just to write down this thing. The definition of min-max of A, right? So it's minimize min of like a min of F, which is distribution over columns. So now distribution over column, this is the distribution over ST path. So what is distribution over ST path? You can think of it as a flow, ST flow, right? Any collection of ST path, when you sum it up, it's just ST flow. So this is like distribution of columns, of path, means of distribution of path, and then max of one edge. And then you get this game, A of FE. Okay, so now this look okay. How to even interpret this? What is this, right? So let's see. You can also write it down like this. A of FE. I claim that this is just like the total value of A of FE is just the total value of the flow on HE. I claim. So let's see why. Like we can calculate this. So A of FE, right? This is just you can think like this is just a vector that for an HE, and then you multiply it to this A, and then you multiply it to vector F. This is just the definition of this. So note again, this is the distribution. This is not a distribution. Oh, it should be E of F. Sorry, EF. Okay. So then this is what? Let's just like can say that summing over all edge E prime in E and path P in overall path, right? And then we can say that this is just one. Let's say this is an indicator whether an edge E prime is E, and what's the entry of A? It's just, let me write this, indicator whether an edge E prime is in the path P. This is just A of E prime P. And then F, this is just kind of, we can think like, what's the entry of FP, right? This is just basically FP. So the flow, like F is just like a collection of paths. This is like a value of the flow along this path P. of flow along path P. And you know that the sum of P is 1 because F is a distribution of path. So this it's just like the total value over all path is 1. That's what it means to be distribution. Right? So are you with me up to this point, this calculation? Right? And then once you have this, like, so this means that you just sum over only when E prime is E, right? And only when E prime is in P. So this is just the same as summing over all E in P, FP. That's nothing but like the flow value in E, the total flow value along the path, along that goes through an HE. Okay. Question about this? Is good or not good? Yeah.
Are we summing over all paths for a fixed E?
No, this is yeah. Summing good. Summing of all paths such that E is in P.
Okay.
Maybe I can write, yeah. Right. Yeah, the way to write this down maybe is like still summing over all paths. And you get FP, and only when E is in P. So only the path that goes through an HE. And that's FE. Right, make sense? More question. There's gonna be like a calculation like this in this class. So I want to make sure that you at least that you are with me in the first example. Should I go on? Right? Okay. So now that we have interpreted it, min max of A is min F max E FE. So what is this? Let's interpret. Let's read this again. So I claim that it's just you can think of this as a problem where you can think of it as minimum congestion flow, right? It's a problem of finding ST flow that minimize this whole thing. And what is this whole thing? It's like this whole thing is the maximum congestion over our edge. Like you can think like F of E is just how much flow go through an edge. That's the congestion on an edge. We want to minimize the maximum congestion on every edge. So we want to find ST flow such that the total unit of flow is 1 because this is the distribution of path. So when you sum over all value of the path, that's just 1. And we want to minimize the maximum congestion. So that's minimum congestion flow. But if you think about this is actually the same problem as one problem that we have seen, that we have learned about. This is just the same as max flow problem. So let me compare it to max flow. Okay. What is max flow problem? Let's say when the edge have unit capacity, right? For max flow problem is to find ST flow, that maximum with maximum value, but now you cap the maximum congestion to be 1 because the edge capacity is 1. So you see that this is like really symmetric. Like here you cap the value of the flow to be 1, and then try to maximize minimize the maximum congestion. Here you cap the congestion to be 1, and then maximize the value. Let's see that one example, right? If you have this graph, right? It's just a graph with 3 paths. Then what's the best flow what's the best minimum congestion flow in this graph? You would just like choose one path here and put it like a 1/2, put another path here, put 1/3. So it's just a collection of 3 paths. That's the best. That's the best way to send 1 unit of flow that minimizes the congestion. And now if you just scale it up such that the congestion become 1, then you will get the maximum value. That will be your maximum flow, right? Because now the congestion is as small as possible here. So if you force yourself to scale it up so that the congestion is 1, you will get the maximum value. Make sense? So they are really the same problem up to scaling. Like for here you force that the capacity is at most 1. For here you force that the value is at most is 1, and you try to maximize the flow. Right? They are the same. Okay. So in other words, like suppose that you have computed the best congestion for minimum congestion flow. If you want to answer max flow, just return like 1 over the best congestion. Here the best congestion is 1/3. Just return 1 over 1/3. That's 3. Right? I hope I convinced you that they are the same. So now, let's try to look at min-max. Sorry, max-min. Right. What would be your guess? It should be min cut. So it's always going to be the case that like a min-max and max-min will be dual to each other. But let's try to interpret it directly. Okay. So, okay. What's max-min of A, right? It's a problem of finding the best distribution of edges, best distribution of row, such that it maximizes this whole thing, maximize min of column AXP. And I will not go through calculation carefully again, but you will get that AXP is just going to be like summing over X, summing over all H in P, XE. You can check this. But with this, now we can also try to see what is this problem, right? So this problem You can think like you want to find, this is a problem of finding edge assignment, edge weight assignment x. X is the distribution over edges. So it's an edge weight such that the total weight of x is 1. The sum of the weight is 1. So that's distribution of edges. And what this x should be, it should maximize this whole thing. So, but now when you think of this whole thing, what is this thing? Well, sum of E, H in E, XE. If you think of X as a edge weight, then this is just like a total weight of the path. Right? And then, so what is min over all path of xp? This is like just the distance from S to T when the weight is x. Right? When you want to find like the best path with minimum distance from S to T, that's just the distance from S to T. So it means what? It means that this problem is to find x with total weight 1 that maximize the distance from S to T. So it's like you have like you can put value into edges such that S and T is separated as much as possible. And now I claim that this is just the same again with fractional version of mean cut. Because why? In fractional version of mean cut, right, you also want to find edge weight such that now the distance, the ST distance is 1. And we want to minimize the total weight. That's the fractional version of mean cut. Right? If it is integral version of mean cut, you wanna choose like you wanna choose a set of edges so that like any ST path must go through a cut. Here is a fraction, like so that is like a distance is at least 1. So like every path will go through a cut edges. But here is it's a fractional one, so it just talk about the ST distance. Just put the value into edges so that S and T is like a 1 distance apart. And you want to minimize the total weight. Okay. And you see this is just kind of the same problem up to scaling again. Both problem just want to like make S and T as far apart as much as possible. In this problem, you cap your capacity, like the total value that you can put is just 1, and you want to maximize the distance. And here, for mean cut, you know that your goal is just to separate them by distance 1, but you want to minimize the total amount of value that you put. So they are the same again. So basically, mean cut is just 1, like the value of mean cut is 1 over the value of the game. Okay. All right. Okay, so now you see that start with this innocent looking game, right? They actually capture mean cut and max flow problem. Now suppose that, and so if we want to solve this game, like like if we can construct a strategy for both max and min player, then you will find min cut and max flow. Okay, so let's do it, and let's see how to get the strategy for both min cut and max flow. Okay. So if you don't follow this calculation, that's fine. Right now, all you need to do is that okay, let's say that this game capture min cut and max flow. Let's try to find the best strategy for both min and max player. Okay. And we know that we have two ways to get the approximation of both min max and max min. Right? We have an algorithm that uses min greedy or max greedy. Let greedy and multiplicative with update plate to each other. We have two algorithms, whether the max player is greedy or min player is greedy. So if if you let the max player be the greedy one, then what does it mean? Then the min player will be weight update one. But the min player is like the path player. So he needs to update in each round, he need to update the weight along every path. So that the running time to update the weight on every path would be at least for each round he need to pay linear in number of paths already. So but this is like exponentially large. So that's not a good idea for sure. So we just ignore this. So instead, but we have another way, right? Okay, if max greedy is not good, but let's try min greedy algorithm. So when you use min greedy algorithm, when min player is a greedy one, max player is a weight update one. So max player is the edge player that need to update the weight on every row, which is every edge. So in each round, we will just the max player will update the weight in linear time proportion to the number of edges. So that sounds good. It's just linear in the size of the graph. And then min player need to do something. We will see what he needs to do soon. But then there are a some number of rounds, not too many. So this looks good. This is one that we will choose. And let's analyze what is this thing? What is min greedy? What is the task that greedy need to do? So recall, right? The time for min greedy is just the time to solve this min problem. That is when you fix x, like when row player choose the distribution, fix the distribution of row, then when max player choose the distribution of row, then the min player will choose the best column according to this row, distribution of row. So choose the best path according to x. So now let's interpret this one. It means that the problem is that given fixed x, right? This thing, what is argmin p of xp? I said before that axp is just sum of all edges. Axp is just this thing. So now let me ask you, can you see what is this problem? This is a problem that we have seen before. What is this problem? Given x, which is the number on edges, find a path such that the sum of x along this path is minimized. Anyone? You have a graph and you have number on every edge xe, and you have s and t, and you want to find a path such that the sum of xe on the path is minimized. Yeah.
The shortest distance?
Yeah. It's really just the shortest path problem. It's exactly shortest path problem. So this is just exactly shortest path problem when the weight is x, right? And you know you can solve it. You can solve it in almost linear time using Dijkstra. So you see, even though the number of column in this game, the number of column, which is the number of paths in this game, is exponential. If you want to be greedy, you don't need to pay exponential time. You can just, okay, there are exponentially many paths, but you just want the best path. You want the greedy one. So you just find the shortest path, and that takes almost linear time. So that's the power of sometimes being greedy. You can bypass the size of the matrix, right? So the running time to solve this game, this thing is just e log e. So the total time is just linear times some log factors. And so let me conclude a bit. So what do we get so far? Given the graph, right? You can get a flow with almost minimum congestion. That is, the maximum congestion is at most the best one plus something. And also you get the weight xe such that st distance is almost maximized. Almost maximum is just as good as the best distance minus something. And the total time is just almost linear. And this problem corresponds to max flow. This problem corresponds to mean cut. Time is linear. Now, let's interpret what's going on a bit. When you use min greedy on this game, with game A between path and edge, let me write down what is going on under the hood, right? Just write it down for this game. It just means what? Means that you have several rounds. On each day, the min player be greedy, choose the path, shortest path, according to the weight. The weight can be xt and wt. Xt and wt is just scaling. So let's say I just doesn't matter. I choose the shortest path with respect to the current weight. And then once you choose a path, right? Now the max player need to update its weight on each edge. How did they update the weight? Well, just anything in the path, you multiply it by 1 plus epsilon. And then repeat. And at the end, at the end, the flow is just the average of this shortest path. Okay. That gives you approximate max flow. So you see, and this is such a simple algorithm, simpler than anything we have seen before. There's no residual graph, nothing, just shortest path. And it generalized to not just one, it generalized to multi-commodity flow problem too. It's very robust. And if you think about it, this is really like intuitive. It might be like if you ask someone to solve max flow, when they don't know anything about algorithm, they might actually come up with this one. Why? Because it makes sense. Like if you have a graph, right? And let's say like there is some min cut here. When you try to compute max flow, like when you try to use this algorithm, it will just find some path, right? And then it will just increase the weight along the path. And then basically when the edge here is increased, next time you will try to basically distribute the flow. Like it shouldn't go through this one again. So it will basically try to spread the flow along, like kind of automatically spread the flow along the small cut. So it just makes sense intuitively, and it works formally from this game. Okay. So you see, this is like one of the algorithms that I really like. It's much like so simple and very natural. But okay, first of all, like I want to note that, like you see, what we get so far is not really like we get first of all some approximate flow. It's not the best flow, but also usually we want multiplicative approximation instead of additive approximation. But this algorithm doesn't give you that multiplicative approximation yet, right? It does not give you multiplicative approximation yet, because what we only have is that we get some additive approximation, where like this is just the congestion on each edge. The max congestion on each edge is like almost best up to additive error. So what we want is actually like something like multiplicative approximation. This is just AFE is just FE. Because if you get this multiplicative approximation, it would be multiplicative approximation for max flow as well. Why? Because like this is like you get the flow such that the congestion is at most 1 plus delta value of A. If you just scale the flow down by this value, then it would have congestion like at most 1, so it's a feasible flow with this value. But 1 over value of the game is max flow. So you get the flow such that the value of the flow is almost maximum. So what we want is like a multiplicative approximation, but you see, this is just additive. But this is not a big problem, right? Because if you just set like this 2 epsilon here, set epsilon such that the 2 epsilon is at most delta times the value of the game, then this additive guarantee will be multiplicative guarantee. Just set epsilon to be small enough. And how small do you need? Well, first of all, you know that max flow from S to T, which is the value of the 1 over value of the game, is at most E. So it means that value of the game is always at most 1 over E. So it means that if you just set like so this thing is at most delta over E. So it means that if you set epsilon to be small enough, like delta over 2E, then you're done. You get this 1 plus delta approximation multiplicatively. But then it means what? It means that your running time would look like this. to get this 1 plus theta multiplicative approximation, you set epsilon to be quite small. So epsilon, like by setting epsilon by that choice, total running time is now e cubed. So not that great. Yeah. But it works and it's so simple. And by the way, like there is a way to improve this like easily to e square. But I will not go through it. And I actually show, like in my work, I just improve it to nonlinear using this approach. So this approach that is like nice and simple can actually be pushed down to nonlinear. So it's a nice approach, but like here we just like kind of use like a simple and nice version, like a clean version, like simplest version, and we get this bound. But the state of the art, you can get it to almost linear. And if you want to make sure you understand everything here, maybe you try to define some game, right, that capture max flow with general edge capacity, not just one unit edge capacity. You can try to do this at home. Okay. So now, okay, that's it about one game, path versus edge. You get max flow algorithm and a simplest algorithm to solve max flow we have seen so far. And I think in the whole literature. Okay. So like now you can start like talking about, okay, what if you start consider some other simple game? Let's say when you have a game between vertex and edge. Let's say a vertex player choose a vertex V, and edge player chooses an edge. And an edge player need to pay to the vertex if the vertex is in an edge. Right, one guy chooses an edge E, another guy chooses a vertex. And an edge E will like need to pay to a vertex if vertex is in like if an edge hit this vertex. So if you think like maybe let's try to interpret this like this is when like this player need to choose like the strategy deterministically, right? What would you do if what would you do as let's say as a vertex player? What would you do if you can play randomized strategy? You kind of want to choose distribution of vertex such that any edge need to pay you. Make sense? Like kind of let's think like strategically. Strategically, the vertex kind of want to choose kind of some set of vertices. If there is actually if there is one node here that kind of looks like a star, there's no other edge. You would just choose this guy, and everyone you need to pay you. But now maybe there's no star like that. Still, you need to like want to choose like a set of vertices such that any edge will hit one of your endpoint. So if you need to guess what would be like the max-min problem, yeah, guess. Time to guess now. Like what would be the best strategy for vertex player?
choose the smallest subset of vertex that cover all edges.
Sounds good. Yeah. How about you?
Is it just the vertex cover problem we looked at?
Yeah. Sounds good. Do you have similar idea?
Yeah, what is it?
Something like that. Yeah, actually, you are precisely correct. It's really like finding kind of fractional version of vertex cover, right? But kind of scale it down such that you can only show distribution of vertex, but you want to maximize the extent how much you cover every edge. For the vertex cover, you kind of need to choose fractional, like put the vertex weight so that every edge is covered up to 1 and you want to minimize the total size. Here is just choose the distribution of vertices. Total size 1, but maximize the extent that every edge is covered. Okay, how about edge player? Let's think strategically again, right? So, an edge player, what does it want to do? Okay, it wants to choose distribution of edges such that like, well, it try to maximize because, oh no, it try to minimize. You need to choose this distribution of edges such that like the distribution of this edge shouldn't be like concentrated to any part, to anything. If an edge like a kind of concentrated on one vertex, that's bad. So basically, it wants to minimize like kind of the sum of like it try to choose distribution of edges such that the weighted degree is smallest. Like choose a distribution of edges here such that the sum of YE is smallest. Like a max degree, like look at every node, and this is, for each node there is a weighted degree with respect to the distribution that the edge player choose. That max degree should be smallest. And I let you check that this is just fractional, like just a similar thing to like it's just the same problem to like a maximum matching. Okay. But I will need to skip. Like you can check and like I just put the whole thing here and like you can check. Before I want to go to the next thing that is one of the very nice application of Minimax. It's called boosting. So what I want to do is like let's talk about like some machine learning problem. Okay. And what we're gonna look at is the setting is like, let's say that you have label data point x, y. So it's like x is a picture, y is like whether this picture is a cat or not. Right? So that's like for each picture, is it a cat? Y is like a 0, 1. So data set is just like a set of pictures. Okay. And you have to label whether each picture is a cat or not. And what we want is like some like a predictor that is, okay, function that given any picture, it can say correctly with high accuracy whether that picture is a cat or not. Okay. So with this, like you can define the accuracy of a function with respect to this data set. This is just kind of count how many pictures that you predict correctly. and then average. So it's just a fraction of how much you are correct within this data set D, given the function f. You can also talk about like weighted accuracy. So given the distribution W, right, the sum of W is 1. Distribution over pictures. Now the weighted accuracy of F on D is accuracy of F and D with respect to the weight. This is just basically the same, but now it's like you take the weighted average instead of uniform average. Okay. You can kind of count how much you are correct, but now some picture might have more weight. So you can talk about this weighted accuracy. And what we hope to do is this. We were going to assume that there is some weak learner. Weak learner in the sense that, okay, given any weight, right? Given any weight, then you can find a function h such that at least it is correct by more than half, more than 50% with respect to this weight. So it's just like kind of correct, but not that good. Like correct more than half, but with respect to this weight. Okay. So the fact that you can like choose any weight function, any weight distribution of the pictures, and you can still be correct by more than half fraction. That's like a kind of, that's the strength inside the weak learner. Yeah. So it's not that weak, but it looks weak. But what we want to get is that from this weak learner, we want to construct a simple function f that is just absolutely correct from this weak learner. Kind of just combine a bunch of weak learner, and now everything is correct. And it shouldn't be like combine like a lot of things. Just combine like it just should be simple. Yeah. So that's the goal. Okay. So now let's see how to do this. So is the setting clear? Okay. So now to do this, we will use Minimax, and to do that, we need a game. Okay. So let H denote like a space of function, like a space of function that like given any cat, it mapped to 0, 1. A picture, and it can predict whether it's a cat or not. H denote is space of all function. And now there will be like a player. Okay. The max player will choose the function. Min player will choose data point. And the payoff is just that if like the function on this data point I is correct. Like if you predict correctly, then you get 1. So the max player gains something if it predicts correctly. It's just a natural, simple game. Okay. And now let's see what does it mean? What does assumption about weak learner mean? It means that given any weight, you can find some learner with respect to that weight that is correct by more than half. And I claim that is exactly the same thing as saying that min-max of this game is more than half. Why? Because min-max of the game, right, is just minimum over any weight. When you minimize over any weight, the max, there is a function h such that a of hw, this whole thing, is more than half. What is a of hw? You can check that this is exactly the accuracy of h for this data set with the weight w. I will not go through this calculation, but assuming this calculation, it means what? It means that for any weight that is given to us, you can find some h function such that this thing is at least more than half, strictly more than half. So this thing, min-max, is more than half strictly. That's what it means to assume that there is a weak learner for any weight. Okay. But now, what we can do is just to apply the hard direction of Minimax theorem, because what do we mean by hard direction? Because you know, like we show trivially that max min of A is always at most min max of A. That's like a trivial direction, easy to prove. But using this multiplicative with update thing, that's when we are able to show that max min of A is actually at least min max of A. But min max of A is at least 1/2, more than 1/2. So max min of A is more than 1/2 too. So now let's interpret what is this. What does it mean to say that max min is more than half? It means that just write down what is max min of A. Max over some distribution of function. Okay, max over P is distribution over functions. Min I, Pi, A, Pi is more than half. So it means what? It means that the exists of some distribution P star over function such that this whole thing is big. So there is a P star such that min of this, min over all I is more than half. Let's interpret this right? It means that P star is such that for every I, for every data point, right? When you look at the weighted average of function according to P star, it labels xi correctly with more than 51%. Or to say it in the math way, if you start with P star, which is the distribution of function, and P star h is just the probability mass on function h, then for every I, right? For every I, when you sum over the weight of the function that predict correctly, that's more than half. Sum over the probability mass from P star of h that predict this data point correctly. That probability mass in total is more than half. Make sense? Okay. And can we construct P star? Maybe not quite, but we can get an approximation of P star because we have weight update algorithm that construct the approximation of the best strategy for both player. So let's construct it. If you use max greedy algorithm, then what happened in each round? Well, the min player will choose distribution of data points, right? Then max player will choose be greedy and basically choose some weak learner that is good for this distribution of data point. It will choose some weak learner h such that this is more than half. That must exist because we assume that, and max player is just being greedy. That's what happened in each round. And at the end, max player will just return some distribution P prime, which is just the average of what he chose so far. So it's just average of the weak learner on each round. That will happen. And now if you choose epsilon to be just some small constant, then this max greedy algorithm will guarantee that the distribution that we return at the end, right, p prime, is just going to be such that this thing is almost as good as p star. Like, if it is p star, then this thing is like a 0.51, but you have now some approximation here. But you set epsilon to be small enough, so this is still like a more than half, strictly more than half. That is, for every I, for all I, the total mass that of function in p prime that predict the data point I correctly is still strictly more than half. So far, doesn't look that good yet, but we are almost finished. And by the way, note that like this p prime here is like a simple distribution, right? Because there are just how many rounds does the algorithm takes? The algorithm that we have this is just log n over epsilon square, and epsilon is constant, so it's just log n. So p prime is really just average over log n many weak learners. It's simple distribution. It's not like crazy distribution. It's just take the average of log n weak learners. Okay, now like you have log n weak learners, and now for each data point, more than half of these weak learners will predict this guy correctly. Now what do you do? What is the last step you want to do to get another function that is perfect on every point? Yeah.
Just go with the majority.
Exactly. For every point, you have log n weak learner that more than half of them predict correctly. So if you want, like, maybe for another point, the set that is correct is different, but it's still that set is still more than half. So if you just take majority point wise, you're done, right? Just set. Actually, you don't need to have weight, but yeah, just define the majority function according to p prime, and say that you predict it to be 1 if more than half of the weak learner say that it's 1. And now you're done. You get a strong learner. Everything will be correct. And you see, like this function is just a majority over log n guys, assuming that you have weak learner. Simple but strong, right? Okay, so basically, this should be. I think this is the last thing that I will teach, the technical content in this class. And next time we will I will just summarize what's going on and maybe tell you a bit about what's beyond this class. And yeah, good luck with the exam. Okay, see you next week.